It is my great pleasure to speak here. And today I'm going to talk about my recent work on the Chowla-Selberg phenomenon over function fields. And in the beginning, I'll briefly review the classical story on special gamma values. Then I'll jump to the function field settings and introduce three types of gamma functions and state my result on an analog of the Land-Rollage conjecture. The result is proved by an interpretation of these gamma values in terms of certain CM periods, and I'll discuss this in the language of distributions. And in the final part, I'll apply the connection between CM periods and special gamma values to discuss the Chowla-Selberg phenomenon over function fields and prove Taku's recipe/conjecture for CM dream field modules. And so let me start with the classical case. So in order to solve the interpolation problem of factorials, Euler introduced the gamma function to be this integral, which is originally defined for the positive real numbers. And this integral also converges absolutely for complex numbers with positive real part and satisfies this functional equation. So we may extend gamma s to a meromorphic function on the whole complex plane with simple poles at non-positive integers. Moreover, we have this Weierstrass infinite product expansion of the gamma function, where the small gamma here is the Euler-Mascheroni constant. And so we may use this Weierstrass expression of the gamma function to get like the reflection formula due to Euler and the duplication formula due to Legendre, which is a special case of the multiplication formula due to Gauss. And in particular, if we focus on the special values of the gamma functions at rational numbers, then these formulas gives us the following monomial relations. For each rational number x, which is not in Z, then gamma x times gamma 1 minus x is equivalent to pi. Here, alpha tilde pi, alpha tilde beta means that they differ by an algebraic multiple. And the multiplication formula says that a rational number x such that its n-multiple is not a pole of the gamma function for a given integer n, then we have this relation. So on the other hand, notice that for each real number x, let this diagonal bracket of x to be its fractional part, then it is invariant under translation by integers. So viewing this diamond bracket as a function on R quotient Z, we have the following two relations, which are very similar to the relation of special gamma values presented before here. And so, as you can see, the first one is like the reflection formula, and the second one corresponds to the multiplication formula, where these numbers occurs in the exponents of pi here. And there is an intrinsic relations between them, and I'll explain this in the function field setting. And another remark is that if we define gamma bar to be the map from this quotient group Q mod Z to C cross mod Q bar cross, which is induced from the special values of the gamma function as fractions normalized by the square root of pi. Here Q bar is the algebraic closure of Q in C. Then this gamma bar satisfies this odd distribution property, like this too, and reformulating the previous monomial relations. So one natural question here is, are there more algebraic relations among these special gamma values? And so the conjecture of Land and Rolich predicts that the above monomial relations generate all algebraic relations among these values, which is equivalent to the following statement. Given an integer n greater than 2, then the transcendence degree of the field generated by pi and the gamma x over q bar for x lying in 1 over nz, then the transcendence degree is equal to 1 plus phi n over 2, where phi n is this Euler phi function. And so in this conjecture, one side inequality here is easier because we can use the monomial relations presented before to drop out sufficiently many elements in this generating set. However, the inequality in another side here, this part is difficult. And one reason for studying these special gamma values is their relations with abelian CM periods. For instance, let me recall the Chowla-Selberg formula. Let K be an imaginary quadratic field over Q with discriminant D less than -4 for simplicity, then the Kronecker limit formula implies that the log derivative of the Dedekind zeta function of K at s equal to 0 can be expressed by this, where the pick OK is the class group of K, and for each ideal class A, we take ZA to be a point on the upper half plane so that the corresponding lattice presents this ideal class A. And delta is the modular discriminant function expressed by this infinite product expansion. Here we normalize it by this 2 pi to the power square 12. And on the other hand, Lurch's formula gives another expression of this log derivative involving this twisted sum of the log absolute value of these gamma values, where this chi k is the quadratic character associated to the quadratic extension k over q. So combining these two expressions here and this one, we get the Chowla-Selberg formula here. And in particular, if we let E be an elliptic curve over Q bar, which has complex multiplication by the imaginary quadratic field K of Q, then the left-hand side of the Chowla-Selberg formula, this part, is equal to a non-zero period of E raising to this power up to an algebraic multiple. Hence, we may rewrite the Chowla-Selberg formula into this form, expressing the bar pi as this twisted product of the special gamma values with suitable power of pi here and up to algebraic multiple. And in a function field case, we may also derive the formula 1 here using a Kronecker type limit formula in my previous work on parabolic Eisenstein series on GLN. However, taking absolute value in the function field settings means so much information in the transcendence aspect. So how to take off this absolute value and get a second formula over function fields? This is my motivation to work on this topic. So the goal of this talk is to describe the whole picture in the function field settings and clarify the relations between abelian CM periods and special gamma values in positive characteristics. Okay, so is there any question? So if not, let me move to the function fields. So let me fix up some notations. Let capital A be the polynomial ring with one variable theta over a finite field Fq with Q elements, where Q is a prime power, P power of a power of a prime P, and small k be the fraction field of A. And consider this absolute value on K corresponding to the infinite place, which is normalized by this way. And K infinity is the completion of K with respect to this absolute value, which can be identified with this Doran series field. And C infinity denotes the completion of a chosen algebraic closure of K infinity. And K bar is the algebraic closure of K in C infinity. So comparing to the classical setting, this corresponds to integers, rational numbers, real numbers, and algebraic numbers, and complex numbers. Now let me introduce the gamma functions in the function field setting. In the function field world, we have three analogs of the gamma function. The first one is called arithmetic gamma function, introduced by Gauss, which interpolates the so-called Carlis factorials. More precisely, for each non-negative integer n, consider its quadratic expansion, and the Carlis factorial n is defined by this product, where dr is the product of all monic polynomials of degree r in A. Then Gauss gave the following interpolation. For each p-adic integer y, then write it in the quadratic expansion, then the arithmetic factorial function is given by this infinite product of 1 unit. Here we normalize by the here. So this becomes 1 unit in C infinity. And the arithmetic gamma function is given by this shift. Just like the classical one, we need to shift 1. Notice that this arithmetic gamma function is from p-adic integers to K infinity. And when we consider its special values at rational numbers, we have these relations when we write the fractional part of negative y as the finite sum of with yi between 0 and q. And the value at 1 minus a over q minus 1 is equivalent to pi tilde to the power a over q minus 1. Here, this pi tilde is the Carlis fundamental period defined by this infinite product in C infinity. And this is an analog of the period pi or 2 pi I in the classical case. And it generates the period lattice of the Carlis margin. From these relations, Gauss gave the following analog of the reflection formula and the multiplication formula on special values here. So as you can see, this is pretty much similar to the classical one. On the other hand, Thakur defined the following geometric gamma function, which is analogous to the Weierstrass product of the classical gamma function. Note that this is a function from C infinity to C infinity. Thakur also derived its reflection and multiplication formula. And we state in this form on the special values at rationals. And notice that the reflection formula here looks like this because we have q minus 1 signs in our setting. A cross, you guys move it to FQ cross. And finally, come to ideas, Gauss introduced these a two variable gamma function. One variable is in C infinity, and another one is in ZP. This might be viewed as some kind of generalization of the arithmetic and gamma and geometric ones from these two relations. here and here. And notice that the version here is one of Takuo's modification, which is a bit different from the original definition by Gauss. We take the version here to make the formula cleaner in our study. Also, Gauss and Takuo derived the corresponding formulas like the translation formula and reflection formula, and also multiplication formula here. The second one tells us the corresponding formulas with respect to the variable y, just like the case of the arithmetic gamma function. Yeah. And so the first theorem of this talk is the following analog of the Land-Rollage conjecture. Given a monic polynomial n and a positive integer L, then the transcendence degree of the field generated by three types of gamma values over k bar when x lies in here and y lies in here, the degree is equal to 1 plus L minus 1 over Q minus 1 to the power epsilon n times the cardinality of this multiplicative group. Here epsilon n equal to 1 if degree n is positive and 0 otherwise. And similar to the classical case, we can use the previous monomial relations to drop out sufficiently many generators. Hence, this theorem is equivalent to say that the monomial relations mentioned before actually generates all algebraic relations among these three types of special gamma values. And we remarked that the algebraic independence of geometric gamma values was determined by the work of Anderson, Brownell, Papanicolaou, or ABP, and the arithmetic one was determined by the work of John Papanicolaou and Takuo and Yu, CPTY. And as I mentioned in the beginning, the main ingredient of the proof of this theorem is the close relations between these special values and CM periods over function fields, and I'll discuss them using distributions. So let this FQT be the rational function field with another variable t, and G be its absolute Galois group, and fix an FQ algebra embedding nu from the separable closure of FQT into C infinity by sending t to theta. And G infinity denotes the decomposition group of the corresponding infinite place in G. Then a Stigl-Berger function on G is defined to be a locally constant Q-valued function on G, satisfying these two conditions. First, it is right invariant by the commutator subgroup of G infinity in G. Yeah. And the second condition says that this integration along G infinity is a constant. In the classic case, the G infinity is just the identity and complex conjugation. But here we are in the non-Archimedean case, so we need to generalize our complex conjugation here. So the most trivial example of the Stigl-Berger function is the characteristic function G. And this is invariant under every translations. So this is a trivial example. And other examples come from the CM types. More precisely, let K be a CM field over FQT. Here, in a function field case, we mean that K over FQT is separable, and every place of the maximal totally real subfield over above the infinite place not split in K. So it's like maybe K plus and FQT, and the infinite place splits completely here, and non-split here. Okay, so it's our CM field. And we first identify the cosets of the corresponding Galois group for HK with embeddings from K into C infinity. And we let IK be the free abelian group generated by these embeddings. Then a CM type is a sum like this, where the restrictions of these embeddings, to K plus, the maximal total real subfield, gives all embeddings from K plus into C infinity, sending T to theta. So when this commutator subgroup is contained in HK, then the sum of the characteristic function of this coset is actually a Stiegelberger function. So this is another example. And actually, in fact, we can show that all Stiegelberger functions come from CM types of CM function fields. More precisely, that IK0 be the subgroup of IK generated by all CM types of K, and SG over HK be the subspace of Stiegelberger functions invariant by the action of HK. Then the above construction induced this isomorphism. And since for every subgroup H of G, a finite index containing this commutator subgroup, the corresponding fixed field is actually a CM field of FQT in our definition. And then we may obtain the following isomorphism between the space of Stiegelberger functions and the direct limit of the subgroups IK0. So we have this another description of the space of Stiegelberger functions. So next, let me briefly recall the pre-period distribution. Let K be a CM field whose Galois group contains this commutator subgroup. Then we have a group homomorphism from IK0 to this quotient group. And we may regard this as a Q vector space. And we send every CM type symbol, where the small C nu is the restriction of the fixed embedding in the very beginning to K. And this symbol is an analog of the Shimura's period symbol, and constructed in my previous joint work with Brownell, Zhang, and Papanikolaou. These symbols come from the periods of CM dual T motifs over K bar, just like the classical ones coming from the periods of CM abelian varieties. Moreover, these symbols satisfy certain fundamental properties which are very similar with the classical ones, like inflection-restriction relations, comparing to different CM fields. I'm very sorry that because of time, I'm not able to say more details about this work. But one thing I want to mention is that this inflection-restriction relation among period symbols allows us to extend our map to this direct limit. Therefore, combining with the inverse of the previous isomorphism with the space of Stiegelberger functions, we get an analog of Anderson's period distribution. Note that the condition here, this one, is nothing to do with the period symbol. This is only used in the previous isomorphism here. And the main result of my previous work with Brownell, Zhang, and Papanikolaou on the function field analog of Shimura's conjecture on period symbol can state as follows in the situation here. Let K be a CM field whose Galois group contains this commutator subgroup. Then the field generated by these over K bar where phi runs through all these Stiegel-Berger functions in here is equal to 1 plus 1 minus 1 over this degree and times the degree of k over fqt. And note that since the number here is actually the dimension of this space, so this result implies that the p nu, this map, the period distribution, is actually injective. And the bridge between CM periods and special gamma values as fractions are built from the so-called Stiegel-Berger distribution associated to Takuo's diamond brackets, which I'm going to discuss now. And in the arithmetic case, the diamond bracket of a rational p-adic integer y is just take its fractional part as the classical case. And in the geometric case, it's more different. For each Lorentz series x, the diamond bracket is given by this sum, where for each non-negative integer n, this bracket n depends on the first non-zero positive Lorentz coefficients of x. And in the two-variable case, the diamond bracket is given by this way. The first decomposition is like the arithmetic case, and the second one comes from the sum of bracket n depending on L and the I. Then we have the following diamond bracket relations due to Takuo. The reflection and multiplication formulas in the both arithmetic and geometric case, which pretty much similar to the relations in gamma values. And also, we have similar formulas for the two-variable case. Although they look a bit complicated, if we compare with the monomial relations among gamma values mentioned before, you can see how similar they are, just as the classical case. Next, we consider the Stiegel-Berger distribution associated to this diamond bracket. And so, roughly speaking, we identify Zp over Z with the in K bar. Zp over Z is identified with the mu in K bar. And we identify K over A with the Cartesian torsions. Okay. I should mention that in a function field case, there are two analogs of cyclotomic fields. One comes from the roots of unity, and which gives the constant field extension of FQT. And another one comes from the torsions of Cartesian modules, which gives special geometric abelian extension of FQT, called Cartesian cyclotomic function field. And from identifying this with the roots of unities and K over A with Cartesian torsions, we have the natural action star of the Galois group on the Zp over Z product K over A via a particular embedding new one defined before. And so this KNL is the compositum of the constant field extension and a Cartesian cyclotomic function field. And the associated Stiegel-Berger distribution is defined as follows. For each x in K over A and y in Zp over Z, then we define this STARY by the arithmetic diamond bracket, and this defined by geometric diamond bracket, and this defined by the two-variable diamond bracket, and normalized by this arithmetic one. And in particular, this becomes a function on the Galois group G, this this becomes the functions in the Gamma group G. And we show that they are actually Stiegel-Berger functions. Moreover, the diamond bracket relations assure certain distribution properties of these maps. So these maps are from K over A and ZP over Z to SG. And recall that we have the period distribution from SG to C infinity cross quotient K bar cross. So my second theorem is that their composition, these two, are actually coincide with the distribution coming from the corresponding special gamma values from the by the corresponding gamma hat. Yeah. In concrete terms, the gamma distribution are induced maps from the gamma special gamma values, and more precisely, the precise definition is here by this gamma tilde. As you can see, this takes the fractional part of x, and this is like the fractional part of y. And theorem 2 is actually an analog of the Lin's result. And the proof of theorem 2 needs to express the special gamma values in terms of the periods of certain CM dual T motifs, where the CM field is the cyclotomic function field K and L. For some N and L, then the explicit construction is a generalization of the soliton dual T motifs in ABP and CPTY mentioned before, where the constant field extensions needs to take into account. In combining with the classical case, comparing with the classical case, the soliton dual T motifs play the role of the Jacobians of the grammars. But because it's too many notations, so I'll skip the proof here. So now we can give a sketch proof of the Land-Rollage conjecture in theorem 1. So first, from the L evaluator property of these Stiegel-Berger functions, STXY, which I'll go back to this data, we can show certain universality of our three types of a Stiegel-Berger distribution. And as a consequence, if we let HNL be the Galois group of the NL cyclotomic function field, then this Stiegel-Berger space is in fact spanned by this STXY, where XY run through these elements. Therefore, so the transcendence degree in question is equal to the transcendence degree of this field over K bar, using this only fractional part of the X and Y. And this just from the translation property and the definition of gamma tilde. And the second equality actually comes from the theorem 2 from this equality. So we replace this by this, and also the previous equality here. The whole space equal to this. So we can only consider, so we get this equality. And the third equality comes from our result on Schmar's conjecture of function fields, which have a concrete description of the transcendence degree. And we get the final equality because K and L is a cyclotomic function field, and we know the degree of each terms here. And so this completes the proof. So now we have sufficient tools allowing me to quickly explain the Chowla-Selberg phenomenon over function fields. Recall that for monic polynomial n and a positive integer L, this Stiegel-Berger space is spanned by these functions STXY, where x lies in here and y is in here. So if K is a CM field contained in K and L, then we have these inclusions between Galois groups and also between the Stiegelberger spaces. Hence, for each generalized CM type C of K, where this generalized CM type just a sum of CM types, then the corresponding Stiegelberger function can be written as a linear combination of this, because this lies in here, can be written as a linear combination of these functions. Therefore, the corresponding CM period is equal to the associated product of the special gamma values here. And from the equivalence between Anderson's dual T motifs and abelian T modules, I can present my third theorem here. I'm sorry again that I won't give the precise definition of T modules and dual T motifs, but you may consider abelian T modules as an analog of the abelian variety in the classical case. So if E rho is a CM abelian T module over K bar with the generalized CM type KC, and K is a subfield of K and L, then the space of quasi-periods of E rho is spanned by this product of special gamma values, where rho runs through this coset. And in particular, if E rho is a dream field module over K bar with full CM by an imaginary field K contained in a cyclotomic function field, K and L, then when we write the characteristic function of HK as this combination, then every non-zero period of E rho is equal to the corresponding product of gamma values as fractions and up to algebraic multiples. So although the coefficients mxy are not unique, because the expression here may not be unique, but we have a very concrete way to write them down and derive a Chowla-Selberg type formula. And the key point is the evaluator property of the Stiegelberger function, Stxy. So we may rewrite each character in terms of this very explicit expression. This comes from the L evaluator property of Stxy. And on the other hand, for every phi in SG, we can, using the inner product with characters, to get these expressions of phi in terms of combinations of characters. And plugging this expression into here, we obtain the expression of phi in terms of the Stiegelberger's functions here. More precisely, if we let this NCGAI to be this particular sum, which, because it runs through all these Galois conjugate, it becomes a rational number, then this phi is actually, it can be expressed by this form. Note that these coefficients are rational numbers. So when taking phi to be the phi KC from a generalized CM type in theorem 3, then from theorem 3, we obtain the following Chowla-Selberg formula. So keep the notations in theorem 3. The space of quasi-periods of E rho is spanned by this explicit formula, explicit product of special gamma values as fractions. In particular, if E rho is a CM dream field FQT module, then every non-zero period of E rho can be expressed by this product expression up to algebraic multiples here. And the expression exponent here is defined by here, which is a rational number. And although this looks a bit complicated, but when we look at some special case, it becomes very similar to the classical one. So first of all, when the CM field is just a constant field extension, then our formula coincides with the Takuo's previous result, although he stayed in a different form. And also Takuo also derived this particular case, the Karis T torsion. And note that if we consider the case when K is an imaginary quadratic extension over a QT, where the infinite place is temporally ramified in K, then we may embed K into some cyclotomic function field KD2, where D is the discriminant of K. So in this case, the exponent in this formula has this concrete term. We can derive this one, and our Chowla-Selberg formula becomes like this, which is very similar to the classical one mentioned before. And so, because I still have time, so let me discuss further development. So the geometric reinterpretation of the Chowla-Selberg formula by Gross actually leads to the so-called Deligne-Gross conjecture on the periods of algebraic Hodge substructures with multiplications by abelian extensions of Q. And this conjecture is still wide open, only few cases are known. And in a function field case, applying the work of Arthur Jussica and Pick on the Hodge conjectures over function fields, we are able to state and prove an analog of the Deligne-Gross period conjecture here. More precisely, if we let M be a pure uniformizable dual T-motive over K bar, and HM denotes its Hodge-Pink structure. I'm sorry again that I'm not able to give you the detailed definition. And that H be a Hodge-Pink substructure of HM, which has full CM by K, where K is contained in a cyclotomic function field, say K and L, then H can be regarded as a dimensional 1 vector space over K. And if we view this underlying space H base change to C infinity as a subspace of the Durand space of M, then we may take an eigendifferential omega corresponding to an embedding of K into C infinity and satisfying this equality. Then when the omega is algebraic, which means that this actually in the algebraic Durand space of M, then its non-zero period integration actually can be expressed into a product of gamma values, where the exponents can be determined by the alpha omega embedding and the composition of the Hodge-Pink type of H, written as the decomposition as a combination of Stiglberger functions. So this theorem says that every abelian CM periods in our setting are indeed generated by special gamma values, and the expression can be very explicit from the decompositions of the corresponding CM types. So in the final part, let me talk about my current joint work with Jieyu Zhang and Jing Yu on the Viadi counterpart. And following the Morita's construction in the Piatti case, Gauss also introduced the Viadi arithmetic gamma functions, while the modified Karis factorials here. Here, the modified Karis factorials, this div, are drop out the v part, and moreover, Gauss also derived the functional equation of these Viadi arithmetic gamma functions Moreover, Thakur established a gross Copley type formula connecting some certain special values with the arithmetic Gauss sums and providing some algebraicity of certain V-adic values. And our current finding determines the following transcendence degree of the field generated by these V-adic gamma values, which implies that all algebraic relations among these values are actually generated by ones come from the functional equations and Thakur's analog of Gross-Copley's formula. And as the previous case, one side inequality is easier, coming directly from the known relations. And to show the opposite inequality, we actually express these V-adic gamma values in terms of the V-adic crystalline Durand periods of Collins T motifs with Cm by the constant field extension. And then we play the switching V and infinity trick in the function field case so that we can apply Papanicola's theorem on the Grothendieck period conjecture to get the sufficiently algebraically independent elements in this generating set. And you can see here we need to minus here actually comes from the Thakur's Gross-Copley's formula. And moreover, the V-adic geometric gamma function also introduced by Thakur. And my student Tsing Wei extends Thakur's idea to define the two-variable one. And recently, Tsing Wei just shows a Gross-Copley type formula connecting particular V-adic geometric gamma value to some geometric Gauss sums, also for the two-variable ones. So in this project, in this direction, our ultimate goal is to establish the whole Chowla-Selberg phenomenon for the V-adic Cm periods in a function field context. And so this is the end of my talk. Thank you very much for your attention, and sorry for end up earlier.